So once we start using integrals to find volume, we can find the volumes of all kinds of bizarre, interesting shapes. We completely multiply our power to find volumes well beyond what we knew in geometry. So we're going to talk about first a category, volumes with known cross sections. And so this means that we have some kind of shape like this, and if we take a cross section, that is to say, if we just slice it right through the middle, then what we're going to get is a shape that we expect. So here, for example, we're showing something that has a cross section of a square. And in fact, anywhere that we sliced it in the middle, including at the ends, it has a cross section of a square. And so there are a few conditions here. The base has to either be a function or a pair of functions. You could have an f of x and g of x determining the shape of the base. The cross section has to be some relatively simple geometric shape, a square often, maybe a circle or a particular kind of triangle. And very important, the cross section must be perpendicular to a central axis. And that axis, so that axis would be here, for example, that axis is the line along which we're going to integrate. And so, for example, if this is the x-axis, we're going to conduct the integral in x, and what we're going to have at every point from this simple geometric shape, we're going to be able to figure out a function a of x, where a of x is the area of the cross-section at position x. So it'd be the area of the square of that particular size at that value of x. And then, of course, that slice has a little volume. We could say it has a differential volume of ax times dx, where dx is the width or the thickness of the slice. And so we just integrate this. So v equals the integral of ax dx from a to b, where of course a and b would be the starting points. So in the next video, I will show a numerical example of applying this idea of finding volume with a known cross-section.